Okay, I think we can begin. So, hello everyone. Thank you for joining for the first New Technologies in Mathematics seminar of 2025. And today we're very happy to have Omar Salemohamed who is a PhD student at University of Montreal, and Mila. And he'll be talking about discovering data structures. So, Omar, take it away.
Thanks, Hugo. Thanks, everyone, for having me. Today I'm going to be talking about how we trained neural networks to learn data structures. Um, this is going to be a relatively informal talk, I think maybe less theory heavy than what you guys might be used to. Mainly going to be just showing you some plots that I think look nice. Please feel free to interrupt me during the talk if anything's unclear. Yeah. Okay. So the agenda for today is first I'm going to give you some motivation. So why would we want to, learn data structures with neural networks? Then I'll discuss kind of the framework or the model that we're proposing to use to do this. We mainly focused on nearest neighbor search experiments, just because a lot of the work on data structures has been focused on nearest neighbor search. So we figured it would be a good test bed to kind of try this model out on. I'll mainly focus on the experiments in that setting. And then towards the end, I'll discuss some of the experiments we did beyond nearest neighbor search. So specifically on the problem of frequency estimation. But I also want to touch on some of the other problems we think that sort of this setting might be, that we think the model might be useful for. And then finally, I'll discuss some of the remaining opportunities and challenges that we see are important in terms of learning data structures end to end. Yeah, and this is all work done with my amazing collaborators, Laurent Charlin, Shivam Garg, Vatsal Sharan, and Gregory Valiant. This was a good experience, but I couldn't have done any of it without them. So yeah, just wanted to thank them. Okay, so just so that we're all on the same page of what I mean by data structures, in the abstract sense, a data structure is just an algorithm that transforms a raw data set into a data structure D. And then we also have a query algorithm Q, which accesses this data set or this data structure to answer some query. And so in general, when we talk about a data structure and the query algorithm, we care about the size of the data structure D and the time complexity of the query algorithm Q. Now, there are other things you might care about too, such as like the construction cost of the data set, of the data structure, or maybe the space complexity or memory of like the query algorithm, but we're not going to be focusing on that as much in this talk. So we're mainly going to be talking about the size of the data structure and how long the query algorithm takes to kind of access this data structure. Here are just some examples of some classical data structures. So motivation. So why would we want to do this in the first place? So the project kind of started out with some of us just wondering, like, is it even possible? Like, so for example, can you train like a neural network to learn binary search from scratch without, giving it some prior on the type of algorithm it should be used or anything? And it wasn't really clear that this would work. You kind of need to learn these two algorithms in tandem, one being like, the thing that constructs the data structure. So in 1D, like the algorithm to sort, and then also the query algorithm, so the binary search algorithm. And kind of these are both sort of discrete operations because they're sort of algorithms. So they're a bit different than like the classical like image recognition setup. So yeah, it wasn't clear that this would necessarily work. And I think that's sort of where this project stemmed from, of just seeing if you could do it. But I think there also are some like good reasons to try and do this. So one thing is that traditional data structures are worst case optimal. And so they're sort of agnostic to the distributions that they serve. And so you might ask if you can kind of learn these things entirely end to end. Maybe you can learn data structures and query algorithms that are adapted for your specific data distribution. And to discuss some of the prior work, so I just want to give you some context where this is coming from. There has been work on learning augmented algorithms. And so these are works that have kind of taken traditional data structures and tried to integrate predictions into those data structures. So you can imagine taking like a sorted list in 1D, and instead of using binary search or some other 1D search algorithm, you can train a neural network to kind of figure out where to start the search. And so this was work from Kraska et al., and this was kind of started work in this direction, I would say. There's also works on like learned trees. So if you know something about like the distribution, the query distribution, can you alter the design of a known data structure to sort of better leverage that information. What we wanted to do in this work was a bit different. We wanted to see if you could learn everything end to end without having any knowledge over or without having to start with any classical algorithm in the first place. Like, can you even discover a classical algorithm? Um, I would say that our work is quite a bit more exploratory. I think one of these things that kind of these learning augmented algorithm papers kind of offer is guarantees in some cases on like runtime, and we kind of don't have those guarantees. I think they're also a lot more scalable. So I think these are things to think of as trade-offs. I think we were just starting out with, is this even possible to some extent? Okay. All right. So I'm not going to go too deep into our specific model. I'm just going to give you an overview of kind of the framework. But if there are specific questions about the architecture or details that I've glossed over, please feel free to ask me about that. So yeah, we kind of think about this whole process as sort of consisting of two models or two steps. One is like a data processing step, and the second is a query execution step. So in the data processing step, you're given some raw data set, which are kind of, you have these n data points, and you want to process them by some network into like a data structure. And that's sort of what you get out here. And then in the query execution step, conditioned on some query, you want to query this data structure. And so you can see in this case, we have like m queries, and these are different query models. So the first query model is conditioned on just the query, and it outputs like a lookup position, and it's a sparse position. So it's just a one hot vector. And then you kind of apply this lookup into the data structure. You look at what's in that position in the data structure, and then that becomes part of your query history, which is denoted by history2. And so you repeat this process of just conditioning on the query and everything you looked up before. And I guess a sort of obvious detail, but sort of important, is m. So the number of queries that you make into the data structure should likely be a lot less than n, or should definitely be less than n. Otherwise, you kind of have this like, you can just do linear search, so it's not really interesting. So the idea here is that by having less lookups than the number of data points, you're kind of encouraging these two models to learn an efficient data structure. I won't go too much into the detail, but this data processing network is effectively a transformer. But in different settings, you could use a different model. We just wanted to try something relatively general. And each of these query models are MLPs. They don't share weights. Towards the end, we tried sharing weights, and that worked well. Two, we just wanted to keep it relatively general. The idea isn't really to create something that's really like the best model you can come up with. It was just to kind of start out with something. And then in terms of like what the data generation process looks like, so how do we actually like train these networks? So in traditional like deep learning projects, when you're talking about having like a single training data set, here like each data point is a data set. And so we have some distribution over data sets. So first we have the size of our data set. So that's some hyperparameter of the size of data sets we want to be able to learn structures for. So that's some hyperparameter n. And then we have some data set distribution p, and we sample data sets from this distribution. So for example, you can imagine like the uniform distribution, where we just sample n numbers, and that sort of that's how we create like an initial data set. And then we also have a query distribution. You can imagine like the uniform distribution for now, though in different cases we have different distributions. You could also imagine the query distribution just involves sampling one of the points from the data set. So you want to find if that actual point, if a specific point is in the data set or not. And then, the nearest neighbor is just the nearest element to the query's nearest element in the data set. And you can kind of use any metric, but we're using the L2, the Euclidean distance between the two of them. Yep. So any questions up until now? Otherwise, I'll start going through some experiments. All right, so let's start with 1D nearest neighbor search. So we tried 3 settings here. First, the simplest was just a uniform distribution. So both the query and the data set distributions were uniform. Then we tried a slightly harder distribution, and I'll kind of motivate why we did that later on. And then we tried a Zipfian distribution. I'll just go through these plots because we're going to be seeing quite a few plots like this. So the first thing, the plot on the left is basically showing kind of how our model performs as you give it more queries. So in this case, we had n equals 100. So data sets were of size 100. And we had 7 queries. So it's roughly enough queries for binary search to be able to solve this problem exactly. And so our model is this end-to-end model. I'll discuss these like kind of ablations in a second. But you can see sort of as you get, as the model sees more queries, it gets a higher accuracy in kind of finding the nearest neighbor. And it does quite a bit better than binary search. And I think the point here that I want to get at isn't that, our model is, special in some sense. It's just that it can leverage distributional information. So if we look at kind of this middle plot here, what you're looking at is on the y-axis is sort of the lookup position. So where does the model look at in this data structure, like which actual position versus what the query is. So basically the model has learned sort of that there is a uniform distribution. And so if the query, sorry, all the queries in this case are sampled from -1 to 1. And so if the query is -1, the model is going to start its search towards the beginning of the list. And so this is kind of the thing that you'd want kind of the model to do optimally. So yeah, this was sort of just a sanity check. And then on the right here, you can see sort of a worked out example of kind of how our model searches. So it's looking for this element with the red cross at the end. And so it starts its search at position 6, and then it sort of moves down. It jumps too far, and then it comes back up. The model in this case is actually just being trained to be optimal at like position 6 at query index 6 here. And so it doesn't really have any incentive. It doesn't need to look at reasonable places for earlier positions, but obviously it's advantageous for it to do that. But yeah, that's just a minor detail. Yeah, and I guess I'll just quickly cover these different other models. So yeah, we compare with binary search, but then we also compare with 2 other ablations of our model. One is like a non-adaptive version of the model. So I mentioned earlier here, I guess, that each query model conditions on its history. So all the queries it's seen before. We tried a non-adaptive version just to see what would happen and to sort of motivate why we need a query adaptivity. Sort of kind of obvious when you think of binary search as an adaptive algorithm. Yeah, so without adaptivity, the model can't really do so well. And this frozen model is a variant where, actually I won't cover that just because it'll go too far into details. So yeah, we can just think of the adaptive and non-adaptive model. Yeah, so that's the 1D uniform distribution. Okay, so that was nice, but our first question is, could we learn binary search? And if you look at this, it doesn't really look like the model has done something like binary search. And so yeah, we were sort of wondering like, sorry, yep.
Does it look like you're doing better than binary search? That's what I'm not understanding.
We are doing better than binary search. So I don't know if you're familiar, but there's an algorithm in 1D called interpolation search.
Yeah.
That does a lot better on a uniform distribution because it knows that the data is uniformly distributed, so it can start its search much closer to where the item is going to be, and so our model learns some behavior like that in some sense.
Okay.
Yeah, this is sort of expected. I mean, it's a good sanity check that the model has been able to do this, and it's not. We weren't even sure that we would get this far because what the model has effectively done here is it's learned to both sort the data, so to put the data in sorted order. So this is what kind of the data processing network has learned to do. And then the query model has learned, okay, if the data is in sorted order, a good place to start looking is sort of where I'd expect it to be if everything's uniformly distributed. So I think, yeah, this is still not super trivial, actually. But yeah, we wanted to learn binary search, so we figured, okay, maybe we're going to have to manipulate the data a bit in order for the model to learn binary search, just to see, if we make the data distribution quite hard, does the model still learn, a good algorithm? So yeah, this is just to show that when things are uniformly distributed, there's a lot of information that you already have. So for example, the first item in the list of a sorted list, when things are uniformly distributed, are normally going to be an element from 0.0 to 0.4. And so the model is basically being able to exploit this type of information. And if you look at on the right, we're just seeing some uniform samples of data sets. So the idea would be like, can we design some harder distribution that forces the model to learn, binary search? So yeah, this was the idea is we did come up with this harder distribution. I'll go over it in a second, but what you can kind of see is that it's a lot less concentrated. So like if so basically the element in the data in position 0 of the sorted list can be pretty much anywhere in this range and so forth with position 1 and 2. And so this makes it a lot more challenging for the model. It can't basically use any prior information. So the way this distribution works is basically we sample kind of a data set like so. So first we sample the middle element, which is like D4, and we have some parameter alpha, which you can just think of as like being like perhaps the number like 100. And that has like a very high variance, a huge range that we're sampling over. So it's a high variance. And so like the middle element can really be anywhere along, 100 raised to 3. And then to sample like the element to the right of that middle element, we then sample from the distribution of uniform, but to like a slightly lower variance in a slightly lower variance region. And we kind of add that number to the element in the middle, and a similar thing to get the element on the left, and so forth. And so that kind of, sorry, that was wasn't the greatest explanation, but the idea is like you want things to be quite to lose a lot of this prior information from this distribution. And that's kind of what you're looking at here, where the middle element can be sort of anywhere in the span. And yeah. And so we found that when we train our model on kind of this distribution, the performance curves look a lot like binary search. And if we looked at the learned algorithms, we can see that we have learned something a lot more similar to binary search. So on the left, you can see some of the queries to our model compared to how binary search would approach this problem. And yeah, we get our model starting in the middle, for example, then looking at sort of the 25th percentile, and then going up or down depending on that. And if you look at like the aggregate, the average of the positions, it looks a lot more like a binary search tree. So yeah, that was just to show that the model can learn binary search, but I think the caveat is you kind of have to push it to learn it. But I mean, I think the good thing is that the model is always doing something sensible. So if you can do better than binary search, the model will learn an algorithm that's better than binary search. Okay. And then the final distribution I'll discuss in 1D is the 1D Zipfian distribution. So this is just when queries follow a Zipfian distribution. So some queries are sampled much more often than others. And the reason I kind of wanted to showcase this experiment was to kind of compare our model to this Zipfian tree, which is kind of a learning augmented algorithm that uses distribution information to augment a tree and to do much better, as you can see, than binary search. And yeah, this is just to say that when you learn everything end to end, you kind of learn solutions that can do sort of similarly to these like learning augmented solutions without having to do this hand-designed, hand-constructed algorithm. So that's kind of nice. I would say a caveat is we lose the guarantees of the Zipfian tree. So I wouldn't say one is better than the other. It's just to show that there are advantages to doing this end to end. Okay, so now that was all our 1D results. I'm going to go into 2D to get things show you a few more interesting results. So in 2D, things are a bit harder. We don't have, there's no natural ordering to kind of the data. And so you can't, rely on algorithms like binary search. Some of you might be familiar with KD trees, and that's sort of kind of the best thing we have agnostic of data distribution. So I'll quickly discuss like how a KD tree works. So effectively a KD tree for two-dimensional data sorts the data on every dimension and then kind of aggregates the tree like that. So for example, the first element in the tree, A, is the middle element according to the X dimension here. So that's kind of how you can see that. And then the next children are sort of the leftmost and rightmost element according to the Y dimension. So you can see that, for example, B and E kind of split A across this dimension, and then you go to the next dimension, which is dimension X, and you kind of repeat this process. So it's a relatively complex algorithm. in the sense that it would be sort of surprising if our model could find this. And so that's why we wanted to, train it on this setting as well. But yeah, so first we started with the uniform distribution. And with the uniform distribution, we were sort of just wondering what it would do. So here you can see points, 100 points sampled. On the left, you just see the raw data set, and the points are colored by how close they are in the input list. So there's sort of a random ordering at the beginning because we just randomly sampled points. But you can see what the data model has effectively learned to do is partition space by how close points are to each other. So points in the sort of the data set that are close to each other are points that are close together in space. So that was just, a nice result to see. And I'll maybe just show you how the model kind of does its queries versus how a KD tree does its queries. So on the left, you can see the KD tree kind of starts for the middle element and then kind of works its way up. And our model starts sort of closer to the actual element because, again, it's using this distributional information. Again, not shocking, but just nice to see that the model is consistently able to leverage this information in, beyond 1D2. Okay, but now we wanted to see if our model could learn something more like a KD tree. That seemed like a ambitious thing to do at the time, just because the construction of a KD tree is a lot less trivial than, for example, a uniform when everything's are uniformly distributed, and it's a lot easier to things are a lot smoother and you can manipulate things a lot more nicely with the uniform distribution. So yeah, to kind of do this, to kind of encourage our model to learn a KD tree, what we did is we took our 1D hard distribution and we just independently sampled each dimension from this hard distribution. And yeah, we can see, if you look at the plot on the right, you can see that, the performance plot tracks KD tree nicely. But also, you can see that the data structures that our model has learned have like non-trivial overlap with that of a KD tree. So basically what you're seeing here is at the top row, let's say like the top left kind of box here, you're seeing what the data structure, so this is a data set of size 15. So you're seeing the average distance between points between different coordinates. So like, for example, the bottom left is just the average distance between, the point and itself. The top right is just, sorry. Yeah, so you're just saying like when points are getting permuted to different positions, what are their average distances? And this is just one way to kind of visualize sort of these learned data structures. And you can see it looks quite similar to that of the KD tree. So we see, for instance, in dimension 1, the KD tree is first kind of organizing based off of this dimension, splitting off of this axis. And our model does a similar thing, but with dimension 2. I mean, it's not like a direct one-to-one, but yeah, it was nice to see that it could do something akin to a KD tree. Yeah, so that's the 2D distribution. So maybe we can go to high dimensions now. So the problem with nearest neighbor search in high D is that we kind of have the curse of dimensionality. So using classical algorithms like KD trees doesn't really work so well because they require an exponential number of queries in high dimensions. And so if you want to do exact nearest neighbor search, you're kind of going to struggle in high dimensions, but you can do approximate nearest neighbor search. So instead of, recovering the exact nearest neighbor, you might have some guarantee that whatever you recover is only so far off the true nearest neighbor some portion of the time. And that's what algorithms like locality-sensitive hashing give you. So I'm going to discuss this algorithm a bit, and then we're going to compare it to kind of this algorithm. So yeah, for those of you who aren't familiar with locality-sensitive hashing, the basic idea is to sample some random hyperplanes in your high-dimensional space. So let's say D equals, in this case, D is just 2 dimensions for the sake of this diagram. So you sample some hyperplanes. Let's say you sample K hyperplanes. And for each data point, you kind of take which side of the hyperplane that data point falls, and you do that for each hyperplane. And so you have these kind of K binary numbers, and that becomes your hash code. So to construct the data structure, you just map each data points to its corresponding hash bucket. And then when you have a query point, you kind of just you compute its hash code, and then you look in the corresponding bucket as well. It's a relatively simple algorithm, but surprisingly, it didn't really. It's a relatively recently developed algorithm. I think it was just came out towards the end of the 20th century. So it took a while for us, I guess, to come across this algorithm. And so we wanted to see if our model could come across something like this in high dimensions. And so what we did is we kind of ran a similar experiment that we ran before, but now in 30 dimensions. And so yeah, I'll kind of show you what our model did here. So effectively, in this case, I'm just gonna, where we actually run our experiment with like n equals 100, but to kind of show you what the model has learned, I'll show you in the case where you just have 4 data points. So basically what you're seeing here is kind of the hash buckets, or the hash functions that the random vectors that our model has learned. So it does learn to do something similar to LSH, where it learns, two, in this case, orthogonal directions, and then basically partitions the space based off of these directions and assigns hash codes. And so basically our model effectively did learn to do an LSH-like solution for small n. I think for larger n, it did do something similar to LSH, but it was harder to interpret like exactly what these random vectors look like. And I don't think it was as clean cut as as of a solution as you get when n equals 4. But if if you look at the performance on the right, you can see our model roughly tracks that of these two LSH algorithms with a different number of random vectors that they're splitting over. Yeah, so that's 30D. And then I'm going to go over our next set of results where we wanted to do something with more high in higher dimensions and really kind of showcase the value of using neural networks here. So the idea with this experiment was to see can the model learn like a good data structure and also features at the same time. So let's say it had to do nearest neighbor search, but where kind of we want to search over some low dimensional manifold, and sort of the search space distances aren't defined in kind of our original high dimensional space, but over sort of this low dimensional manifold. So in this case, to kind of do this experiment, we generated a bunch of 3-digit MNIST images. So you can kind of see them on the right here. And so in this case, the distance isn't defined in sort of the image space, but over the label space. So the model doesn't have any information that that's the case. The only thing that the model sees is for a given data set in a given query, what's the nearest neighbor of that element to the query. And so it kind of has to infer what this low dimensional space is and what the actual metric is. And so going back to kind of our original model here, we're using the same setup, but actually what we do is we have a CNN that we learn in tandem with these two kind of sets of models. And so we pass each image to the CNN, and then the features are what is fed in kind of to the data processing network and to these query models instead of the original images. And so the model now needs to learn sort of these 3 components in tandem with relatively limited supervision. And yeah, so this was sort of surprising. We didn't think it would take off the ground just because, it needs to do all the things it had to do before, but also learn that images correspond to certain labels. And so that's sort of, eventually we found that it was able to do this with relatively small data sets, so with data sets of size like 50 elements. But it was still kind of cool to see this because, there aren't really any other kind of models that we have out there that can do this type of thing. We can see on the right sort of how their model's performance compares to these other algorithms. Now, there's kind of asterisks beside these algorithms because these algorithms aren't really fair comparisons. Like binary search, for instance, can't really do this in the original space, so we're just showing what binary search would look like over the label space. Locality-sensitive hashing can't really do this either because it's not being provided with the right metric. So we're again doing this over sort of the label space instead. And I think the cool thing here is that there has been work out there that has tried to do like learn hash functions, but these are sort of non-adaptive methods in the sense that you just kind of map to your corresponding hash bucket and then search within that bucket. But there's not really an adaptive algorithm. And so that's kind of why this LSH type thing doesn't do as well as like, let's say, binary search in the ideals kind of space. And so like what we wanted to show here is that when you learn everything end to end, you kind of have the best of both worlds of being able to kind of learn a good representation, but also learn some sort of adaptive algorithm. And yeah, on the left here, you can kind of see what our model has learned to do. So it's taken this raw data set of numbers that aren't in order, and it learns to sort those numbers. Yeah. Recognize I'm going a bit fast here. So if anyone has any questions or wants me to slow down, feel free to let me know. Okay. So the next thing I'm going to discuss is using extra space. So one way you can characterize, how good a data structure or an algorithm is by kind of the query complexity. So how long it takes to query that algorithm. But also another property that you kind of want from a good data structure is that you'd want to know that if you were able to give it extra space, that the data structure would learn to use, or the data structure algorithm would use that space effectively. And so that's kind of what we started to ask with these next set of experiments. So we're back in the 1D setting. And basically what we're doing is we're giving our model just 2 queries. But we're increasing the size of the data structure. And we wanted to see, with this increased size, does the model learn to put useful statistics in these like additional spaces? And yeah, we just compared to this bucket baseline that we came up with. I won't go too far into the details here, but to kind of show you what the model has done. So for example, in this extra space position 39, which is just some random position, what the model ends up doing is it puts some sort of local average of items in the data set that are around that position, and so forth for these other things. And so basically a good solution when you have a lot of extra space would be to just kind of put the nearest neighbor for every item in that extra space so that you can kind of have a hashing-like solution. And so that's kind of what our model tends to do as you give it more extra space. But for lesser amounts of extra space, it kind of just does some local averaging, which tends to be quite helpful as well. Yeah, so we did this in 1D. We also did this, I believe, in 30D too. And the model was able to use extra space, which is quite cool. It was a bit more challenging to understand exactly what it was doing in that setting. But yeah, I think it was similar to an LSH type solution, but leveraging kind of the extra space it had. I think this is a cool direction for future work to kind of see like how the model might want to use extra space when you have specific distributions in mind. And I think this is generally less studied in kind of theory. So it would be cool to look at this more. Okay, so that was nearest neighbor search. I think there's a lot to say still about nearest neighbor search that we didn't look at in this paper. Like let's say you want to learn algorithms that can do range queries, or you want to learn sort of these adaptive data structures where you can delete and add items. So I think there's a lot more work you could do in this space, but we wanted to see, can you apply this sort of framework to other problems? So yeah, I'll discuss one other problem that we looked at, which is the frequency estimation. And then I'll touch on some other ways you might be able to kind of apply this framework. So just to give you guys a quick overview of what frequency estimation is, the basic idea is that if you have a stream of elements arriving from some universe and a query element, you need to answer how many times the query element has arrived in the stream. So for example, let's say your stream of numbers is 2719223, and these are at each kind of time step, you also have a corresponding query. And you want to know how many times that query has kind of arrived up until that time step. So for instance, here in the first kind of column, you can see that 3 hasn't arrived yet. And so the count, its corresponding count is 0. 7 has just arrived, so it's 1. Similarly for 1, 4 it hasn't arrived, and then 2 arrives, has already arrived twice, and so you guys kind of get the idea. And this is kind of quite a different setting from our original nearest neighbor setup, in the sense that here we're looking at the streaming setting. And so the reason kind of we chose this setting is we wanted to see if our kind of this framework can be applied to something seemingly quite different. And so we had to adapt our models a bit. The query model setup remains the same, but instead of using a transformer for the data structure model, we instead use just a simple MLP. And so both of these models are just reading and writing to some memory. So I'll go over like a classic algorithm in this space, and then we can kind of compare what our model learns to this classic algorithm. So if you guys aren't familiar with the count and sketch algorithm, we can quickly discuss that. So the idea is basically to have a bunch of hash functions. And then for each item to kind of, let's say you have, I guess here we have 3 hash functions. And so for each item, you kind of take its hash for each of the hash functions. You map to that hash bucket, and then you increment the count in that bucket just by 1 here. And then to query some element to see how many times it's arrived, you look at its corresponding, all of its corresponding buckets, and you take the minimum item. And it's a pretty simple algorithm, but it's relatively elegant. And the minimum kind of makes sense in the sense that you can only ever overestimate things here. You can't underestimate because you're always just adding 1. And so that's kind of why you want to take the minimum. So yeah, we wanted to see kind of if our model can handle this setup too. And so we tried with different numbers of queries. And we had a stream of 100 numbers. Just showing 100 here for simplicity, but this went up to like thousands, and it still worked as well. And yeah, I think the idea is that our model kind of did better than count and sketch. And the reason why is because it was able to kind of exploit some distributional information. So I didn't actually touch on this yet, but the numbers here, or sorry, the stream that we use is actually a Zipfian distribution. So both the stream and queries are sampled from a Zipfian distribution. Per data set, the ranking of elements in that Zipfian distribution is changing. So you can't just learn that, element 1 is always going to be the most frequent element, because like it could be different for a different batch. The thing that's fixed across batches is just that there's a fixed skew. So the model knows that the distribution is skewed, but it doesn't know which numbers or which elements are going to be arriving more frequently than others. So yeah, the natural question is like, why is our model doing better in this setting? And I think what we found is that effectively what the model was doing is it had learned something quite similar to count and sketch, but instead of adding 1, kind of when a new element arrived, it decided to add a number less than 1, which when you have quite a skewed distribution sort of makes sense, because you're going to have a lot of collisions in these hash buckets. And so you can kind of intelligently add a number less than 1 to kind of account for the skew. And so basically we kind of took this insight from our model, and we thought, okay, can we take the original count and sketch algorithm and augment this algorithm to, instead of add 1, add some number less than 1, and see, does this do better in real situations? So yeah, we tried this on a data set, on a IP traffic data set, this KIDA data set. I think it has 30 million IP address traces. And we took count and sketch and we tried different update deltas. And we saw that, the optimal update delta definitely depends on kind of how much memory you have. So as you have a lot more memory, you want things to be more exact. And so you kind of converge towards 1 as being the right update delta. But yeah, we saw in some settings it can outperform sort of vanilla count and sketch by doing almost twice as well. And I think the idea here wasn't that this is some like revolutionary insight, but just again that learning from your data distribution can be useful, and something we probably want to be able to do in practice more often. Yeah. We tried one last count and sketch experiment. So the idea here is, I mentioned before that in the Zipfian distribution, the skew is fixed, but from data set to data set, the actual ranking of elements kind of was being shuffled. So here we wanted to see, okay, if you can actually learn properties, let's say like there are there are specific elements that do arrive more frequently. But to kind of figure out what those elements are, you kind of need to learn useful properties of those elements. And so we kind of did this experiment where instead of having, just one-dimensional numbers coming, you had these images coming where some images, so like images of smaller numbers, arrived more often than images of larger numbers. And so kind of what the model learns to do is, again, it learns features for those images, and then it learns to sort of, this is sort of given like the value of the image, so the digit of the image, or the number, where the model kind of looks in the memory when it does its updates and its reads. So for smaller numbers, which are ones being sampled more frequently here, the model keeps kind of independent, or it keeps separate spaces, I guess, to reduce collisions. And then for larger numbers, it eventually just puts everything in the same bucket, which is again a good strategy if things are very skewed. And you can see, yeah, I don't think it's like a super important comparison, but just like Common Sketch can't really do this because it hasn't really figured out what are the more, what features kind of make up more frequent elements. Okay, so yeah, that's the last of our experiments. Yeah, I went through them relatively quickly, so if anyone has any questions, please ask me. But yeah, I wanted to discuss kind of beyond sort of these two setups, where else we think learning things end to end could be helpful. So we thought of some other problems, such as graph data structures. So let's say you have some input graph and you want to be able to take any two nodes and answer some distance query between those two nodes. On one end of the spectrum, you can just kind of keep the whole, you can just retain the whole graph and use no extra space, and then each time a query comes, kind of run your favorite shortest path algorithm. On the other end of the spectrum, you can kind of pre-compute all the distances between any pair of nodes. And that's kind of this quadratic solution. And then the question is, can you do something better in between? There are some existing algorithms for this, where you kind of maintain hubs, and then you just compute distances between hubs, and then at kind of inference time, you just compute the distance between your node and the specific hub. And so the question is, can our model kind of recover algorithms like this, especially if there are certain distributions of queries that we might want to cater to? You can ask a similar question for sparse matrices. So for matrices where you might there might be a lot of like zeros and you want to compress the matrix in some intelligent way. If like you know how you want to use that matrix, so you know the type of computations you want to make with that matrix, then you can potentially compress these matrices in a much smarter way. So it's sort of another use case. And then finally, this was a bit different from like your typical data structure setup, but I think is an interesting way to think about kind of this framework is like, let's say you have like a decision tree and you want to learn a more efficient sort of statistical model. You can sort of model this as a data structure problem where the decision tree is sort of the data structure. Your query algorithm is sort of simple here. You just kind of follow your decision tree algorithm. So you don't really need to learn per se the query algorithm. But you want to learn a smaller data structure. You want to learn how to compress kind of the statistical model. And I think you can kind of model this with our framework as well. There would be maybe some architectural adjustments you need to make for each of these problems, but at the same time, like transformers are quite widely applied to different sets of modalities these days. So I think, it would be a good thing to just start with a transformer and see we can go from there. So yeah, that's beyond kind of nearest neighbor search. What are some of the types of things you can hope to do here? There are definitely a lot of challenges to kind of learning data structures end to end. As I mentioned at the beginning, our motivation here was much more exploratory to just kind of see if this worked, not to necessarily, advocate for using this in practice or for building something that could be used in practice. But I think it's something to think about. So how could you scale these things up? So most of our experiments were done with data sets of size 100 or 500. Obviously, in practice, you're dealing with data sets of potentially billions of points. I think parts of our architecture are scalable, but I think if you really wanted to scale this up, you'd have to rethink a few things and maybe add a few more inductive biases. such as like hierarchical partitions to sort of make things scale nicer. There's also this question of efficiency. So again, we weren't too focused. We focused on a very specific notion of efficiency in terms of the number of lookups into the data structure. But you can imagine that like data set construction matter, the cost of data set construction matters. And so you want a more efficient architecture to do that. We tried some experiments where instead of using like a quadratic attention transformer, we used a linear attention transformer, and that worked well too. I think it really depends on like the setting you're in. For example, for like a KD tree in 2D with like high dimensions, sorry, in 2D on the hard distribution, you might like need a more advanced data structure algorithm to kind of simulate an algorithm like the KD tree. But in high dimensions, especially when you're not really learning something adaptive, something like an MLP might be fine, where you just need to learn like a good hash function. But yeah, that's another direction that matters. And I think another thing to think about when you compare the kind of these learned data structures is that you kind of lose the provable guarantees that you have with, classical data structures. In practice, this might not matter as much if, you're getting good performance out of these. But there are definitely directions to think about. And some of the opportunities that we think you can this kind of framework or paradigm kind of offers are the obvious one is this opportunity to learn distribution dependent data structures in practical settings. So if you could scale this up, I think that would be really cool, and definitely quite useful. And I think we've sort of seen that to some extent with these learning augmented works with learned index structures being used in practice. Another kind of hope for this framework is to see like, are there other problem settings beyond nearest neighbor search where we don't really know what the classical algorithms are, and can we hope to just kind of plug in the problem to our framework and kind of discover some of these classical algorithms like it was able to do in some of these nearest neighbor settings. And then a final opportunity would be maybe just using this to assist us in our current kind of design of data structures. So you can imagine like a setup where first you train a model to identify like promising heuristics, learn kind of the best way to exploit the distribution, maybe like a space partitioning criteria. You kind of extract that insight by kind of looking at what the model has learned to do. And then you kind of augment, an existing algorithm to do this. And then maybe you validate and you get some guarantees out of that algorithm and you kind of scale it up. So this is sort of similar to like, maybe you could say that this is how you could kind of help out those working on learning augmented algorithms to kind of, this could be like an additional tool to kind of guide their search. So yeah, I think another direction that would be interesting to think about would be kind of when you can't really hope to learn data structures end to end. So I think we found some settings where like if the distribution was too skewed, learning wasn't able to come off the ground. So yeah, I think it would be kind of more interesting to look at this from a kind of a learnability standpoint, and what are the limits here. So yeah, I think that's everything. Again, I just want to thank my collaborators. And if you guys have any questions, please ask me.
Thank you very much, Omar. Are there any questions in the on the Zoom? I
Uh,
think there's no question on chat.
I have a couple of questions. Can you hear me?
Yep, I can hear you.
Oh, okay, good. Yeah, it was a nice talk. There was so the most basic one. I thought I understood, but let me just see if I understood. So you have a distribute, a family of data sets, a distribution, like 10 uniformly sampled numbers, and you're training your end-to-end system on examples from that distribution and then testing on a new example, right?
Yeah, that's exactly it. I definitely should have been clear with that at the
Yeah.
beginning. Let's see. Yeah, so basically we're just we don't really think of like a test set. I mean, we just resample from this distribution.
Yeah.
But yeah, we don't really have a
Okay,
training.
that's right. So it's learned, as you say, it's learned something about the distribution, something about the task, and now you tested it on a new one. Okay, that makes sense. And now in this query execution stage, is let's say the EMF guide, does it see the whole history, or does it just see the most recent? What does it see as its input?
Right. So we tried both, but I think most of the results were me showing you its whole history. Um,
Okay,
but I
okay,
think, you know,
so it's like it's successively more and more inputs in the succession of query networks.
exactly.
Okay,
We did try a version where you didn't do that. So basically, we actually tried a version where we just had one query model, so it was just shared weights, and it only ever saw the last thing from the previous model. So you can think of this sort of like a recurrent sort of type of thing. Um, and yeah, that works too. I think we just wanted to keep things as general as possible to see how things kind of went.
so that also worked, where you just sent in the last query, or you sent in something that came from the most recent, the previous model.
Exactly,
All
that
right.
worked as well.
Well, so the second thing, so like Q2 would produce another output which went into Q3, or that Q3 would see only H2 or H3 and not which was it?
Oh yeah, so there's only one model in the second setup, in this
Right.
other setup. And that model would only ever see the original query, and the previous thing that was looked
Most
up from.
recent stuff. And that also worked just as well.
Yeah, that worked just as well. We didn't try it in every setting, but we tried it, you know, in 1D and 2D and some of the high D settings. And it seemed to work fine. And I think that's how you could hope to scale this up even further. It's just by, you know, doing
Right.
something.
Okay. Well, that's interesting. You know, and did you try testing any sort of like length generalization? You know, like you train it on some size problem, you try it on a different or a bigger problem.
Um, so we tried generalization in the sense of like you train it with like 4 queries, so it only looks at, you know, only does recursive thing like 4 times, and then you know try to do 6 or 7 queries, and that sort of worked. That only works with this kind of other setup that we were just discussing, where you're using the
So,
same
but
model.
it sort of, okay, yeah, those are interesting things. You touched a bit in this in your conclusions about tasks that it couldn't learn to do. So you said that, you know, like some weird distributions, it had trouble learning. And
Right.
were there tasks that it couldn't learn, or?
Yeah, so there's a very specific example. This mainly came up in the Countman sketch setting where I discussed that we were doing everything with like a Zipfian distribution, but when things were like very skewed, um, we found that basically for things to get off the ground, you needed to have like a very careful initialization um, of um, of the data structure model. So you wanted sort of the lookup distributions to the initial lookup distributions to be like roughly orthogonal to each other for each kind of position. Um, because otherwise you got in this, it's kind of hard to explain, but basically learning wasn't able to take off the ground without doing that. It was sort of surprising that in general we didn't see this behavior, but I think once you have more skew, you kind of get this more often. Yeah.
Yeah, I mean, it seems like a very natural class of problems. There must be a lot here to understand in more depth. Yeah,
Yeah,
okay, thank
exactly.
you. Yeah, yeah.
Yeah, it was cool. Like a lot of the stuff that the model's learning is relatively interpretable, because we kind of have these sparse queries. And so yeah, most of the work here was just kind of figuring out what the model had done in every step versus, you know, building a better model.
All right, thanks.
Thank you.
Do you have any more questions? I have a very small one with respect to the MNIST experiment.
Yep.
What happens if you train first just a convolutional network to kind of predict the label, and then on this feature space you train your model? Would it be like a fairer comparison, you think? Because are you giving like the ground truth labels to the binary search on the LSH?
Yeah, so the binary search and LSH are just operating over the label space in some sense.
No,
So they're not,
the true label space. I mean the
they're operating over the label space. So they
okay.
don't even, they're not even like images in some sense. It was just to kind of see,
Goodness.
um, yeah. But the model isn't given the labels at all. It's just being
Okay,
given nearest neighbor information.
I see. Okay, and if you train like one model to predict the labels, and then you train your and then you provide the features, the prediction of that label to the binary search? Do you think it will make for a fairer comparison, or it will be the same?
I would think, yes, so that would presumably do better than our model, right?
A little better, yeah,
Because
because you're giving it more information. Yeah.
So
Okay.
yeah, that should do better. Yeah,
Okay, we're just curious. Thank you.
thanks.
Do you have more questions? If not, let's thank our speaker again. And see you at the next seminar. Thank you a lot again.
Thanks very much.